Greetings, I, Priyal Bhojwani, along with my partner Aadittya Deouskar, will be elaborating on our novel project Advanced Aneurysmal Therapeutical Model, also known as AATM. It is a novel mathematical approach with a correlative computational framework for precisifying aneurysmal therapeutics.
The chronic illness known as abdominal aortic aneurysm or AAA causes the individual's abdominal aorta to diametrically expand until it ruptures. This is a common cardiovascular disease that occurs to over more than 10 million people per year in India, with a high fatality rate of 40% pre-rupture to 90% post-rupture. The rupture of the arterial wall results in organ failure, internal hemorrhage, and
Is
ultimately
currently
death.
prescribed 5 to 6 imaging scans for the monitoring of the abdominal aorta, thus increasing the radiation exposure as well as the expenses. Human estimation for the insertion of stent graft and EVAR surgeries leading to surgery failures, and also human estimation for the rupture date as well as the expansion
Aneurysmal
date.
therapeutical model is a therapeutical model with the primary objective of the elimination of inaccuracy from AAA treatment to reduce the fatalities drastically by removing the human estimation based errors. This involves the use of a single imaging scan to render a parallelly functioning computational framework for real time and accurate monitoring of the abdominal aorta. We use the CT scan of the patient to make a geometrical model of the abdominal aorta, and then use computational fluid dynamics and finite element analysis to render the real-time blood flow in the geometry of the abdominal aorta. Then we derived a mathematical linear regression model which quantifies the expansion rate of the abdominal aorta in t units of time. And then we also validated it using real life value sets to get a accuracy of 95.64% compared to intense research methods. Coming on to the methodology. The first section of the methodology constitutes to the rendering of a one-to-one real-time simulation of the abdominal aortic blood flow in the geometry obtained from the patient's CT scan. The first step is 3D reconstruction. Abdominal CT scans of the patient were obtained from online repositories like NBI database, and then using an open source software 3D slicer for geometrical analysis, the iliac bifurcation of the abdominal aorta was segmented using the segmentation tool. Then using the segments and an appropriate smoothing factor with a volume rendering ROI, a one-to-one 3D model was obtained in a raw geometry format. In order to complete the task of hollowing out the artery for simulation, an additional extension was employed. Then on this geometry, VMTK or vascular modeling toolkit processing was performed for obtaining geometrical values related to the abdominal aorta for the MLR model variables. The second step is the mesh generator. This the obtained geometry in the STL format or the standard triangle language format underwent facet corrections using the GMSH software, which is a finite element mesh generator. After doing so, the refined STL geometry was introduced into MeshLab, where comprehensive checking and repair algorithms were executed. The resultant STL file was then imported into FreeCAD for the conversion of the STL to STEP by the use of part tool. This step file was imported into ANSYS space claim, in which the number of facets were reduced. Then the geometry was imported into SCDOC format in the ANSYS fluent flow, in which two sizing enhancement and one inflation procedure was performed, and the mesh was generated. Now coming on to the third part, which is the rendering of the simulation. In ANSYS Fluent Flow, we created a novel simulation solver which constituted of the system of differential equations named as Navier-Stokes and continuity equations, along with our own novel mathematical linear regression model. This application of the simulation solver in the geometry of the abdominal aorta or the mesh of the abdominal aorta gave us the following three interpretations. Firstly is the velocity streamline of the blood flow in the abdominal aorta. This shows with what velocity are the blood particles traveling in the abdominal aorta in real time. The second is the pressure gradient of the abdominal aortic wall. This demonstrates that the flowing blood exerts the pressure onto the arterial walls, which section the highest. This pressure gradient allows the doctor to accurately insert the stent graft in the endovascular repair surgery to increase the success rate of the surgery, and which precisifies the surgery of the abdominal aortic aneurysm. Then the third is the eddy viscosity in the volume of the abdominal aorta, which gives an accurate value of the volume of the abdominal aorta. Coming on to the third and the most novel part, which is the mathematical linear regression model, which we derived for quantifying the expansion rate of the abdominal aorta in T units of time. We surveyed literature and listed out the following biomechanical determinants that directly contributed to the inertial expansion. Then we modified those. Biomechanical determinants to make them more suitable into the arterial environment. Then we substituted these mathematical determinants into a correlative function of the Laplace's law in the vascular system, which states that the diameter of the blood vessel is inversely proportional to the wall thickness of the blood vessel. Then doing this, we got the following mathematical linear regression model, which uses geometrical values for calculating the expansion rate or the expanded size of the abdominal aorta after T units of time, using which we could predict the time of rupture of the abdominal aorta, thus giving the doctors a deadline to perform a surgery before. For the validation of the MLR model, we used real-life datasets, as you can see here, which were obtained from online repositories like NBI database and the ANURISC repository. We compared the outcome of our expansion rate and the expansion rate which researchers got after comprehensive research and tissue biopsies. So as you can see here, the expansion rate results are quite accurate and giving us an overall accuracy of 95.64% with 5 datasets.
By using the simulation of arterial walls pressure contour, the necessary measurements for the implantation of stent graft were acquired. AATM was able to predict the rupture date and expansion rate with a high
Moving on to the conclusion. AATM will highly reduce the treatment cost and an individual's exposure to radiation by reducing the number of imaging scans from 5 to 6 to just 1. By using statistical data and eliminating the practice of human estimation, AATM will significantly increase the accuracy of AAA treatment planning, monitoring, and the surgeries as well. Our framework will reduce the number of AAA fatalities by improving treatment accuracy and lowering the radiation exposure for the patient. Thus, ATOM framework will be a groundbreaking therapeutical aid involving the use of newly developed technologies such as mathematical studies and computational sciences for drastically minimizing the global fatality. We have consulted cardiothoracic surgeons as well as mathematical individuals regarding this project and have found positive results. And these are the following are the references, and thank you.